now?
Yes, now it works.
Okay, sounds good. All right, let's get started. So, hi everyone, I'm Rafael. It's great to be back. I'm a PhD candidate at Princeton University in the United States. And today I'm going to give you an overview of JAX FDM, a differentiable solver for accelerating structural design at the conceptual stage. But first, why do we care? So as a structural engineer, I'm fascinated by lightweight structures. These are systems that can span long distances with marginal material volume thanks to their shape. But despite their apparent complexity, the key idea behind these geometries is pretty simple. And it boils down to geometries that carry loads mainly under combinations of axial tension and compression. And the quintessential example of this condition is the catenary, the hanging chain, where if you have a chain and you let it loose, the geometry it's gonna find its way to, it's one that is tension only. So if you magically froze that, turn it 180 degrees around, you'll get the complement of that, which would be an arch that works not in tension, but in compression. So while we could go around and build a bunch of physical hanging chain models to generate these structurally efficient shapes, today we have access to a plethora of numerical form finding methods that allow us to compute these geometries in a computer. Perhaps the most popular or the most consolidated numerical form finding method here is the force density method, or FDM. I'm sure that more than one person in the audience has heard or even worked with it. So we like to think of the FDM and of form finding methods in general as a function represented here by the blue box in the middle. Think of a little grasshopper component. And so this function takes two inputs and outputs one thing. The first input is a mesh or a network, or more generally a graph, G, on the left-hand side of the blue box. And the second type of input is a set of continuous parameters, theta, which for the force density method are the force densities Q defined on the bars of the graph, the applied loads P, and the positions of the supports XS. So if you input some graph and a set of parameters theta to the box, then you shake the blue box, then you'll magically get an efficient shape that is compression only, tension only, or combinations of the two, that we denote here by capital X, right? And so this is amazing because with a numerical method like this, we can change for a fixed graph G, we can change different values of the parameters Q, for example, and then we can get, a plethora of different shapes. Like even this very funky, funny looking ones like the X3, which even despite its appearance, is actually another compression only structure. And just for clarity here, we are representing the values of the force densities with the colors here in the Viridis scheme with the color bar. So it's all perfect. We have form finding methods. We can generate a bunch of efficient shapes and everybody lives happily ever after. I wish I could tell you that that is the case, but otherwise I wouldn't have a job. So there are other limitations. There are some limitations of form finding. So what are the challenges? Well, the main challenge is that these digital structures or these shapes do not live in the void, and we ultimately want to build them to serve some major purpose. And building real structures require us to satisfy other constraints. And while structural efficiency is an important condition, it's not everything in it. So to build a structure, we need to find one that is efficient, yes, but that it also satisfies other constraints arising from architectural, fabrication, and even other structural criteria, like, for example, controlling the magnitude of the reaction forces at the foundations of a structure, for instance. But to give you a more concrete example, let's take a look at this slide. Suppose you're interested in generating a compression-only geometry to design a grid shell, but this structure should look a very specific way, like the arbitrary geometry on the left, right? So this is something that, as a structural engineer, you don't maybe don't have much control of. This is something imposed by the architect. And so you just want to find a convention-only shape that, is as close as possible to that. And so for constraint form finding, which is the real goal here, what we actually need to do is to solve an inverse problem that, unlike traditional form finding that goes from left to right, from parameters to solution, here what we actually want to do is to say, okay, form finding, what I need is to find an efficient shape that looks like this other arbitrary shape. And the question we really want to know is, what are the right parameters that are conducive to that? And while there are many approaches to do this, for example, God forbid by hand or using genetic algorithms, we identified that there was a big opportunity to generate these structures in a simplified, faster, and principled approach. To respond to this question, our answer to this question is JAX FDM. It's an open source software crafted with care in the form finding lab at Princeton University. And you can check it out on GitHub. Oh, I think I'm stuck. Oh, okay, here we go. I think I'm back on track. Oh, one too many slides. Okay, yeah, so this is supposed to be a GIF where we show how with JAX FVM, using some secret sauces that I'm going to talk about in a minute, we can automatically take an initial efficient shape from some starting point and progressively, approximate the target shape until some convergence criteria. What happens under the hood, and I promise this is the only one slide I will show math and equations during this presentation. So what we do is that we solve constraint form finding using gradient descent. So to that end, what we do is to formulate and minimize loss or an objective function iteratively. And what this essentially does is that it's measuring the distance between a shape x1 generated by the force density method and a target shape x hat. And then a good solution, or the ideal solution, would be one where the loss function is 0, which would indicate we perfectly matched our intentions. But this is typically not the case. So what we can aspire to is to a best fit solution that is optimal in a least squares sense. So I was talking about optimization gradient based. Here, the secret sauce is how we tune those parameters, those force densities, those applied loads, and those support positions iteratively on convergence. And here, the big picture here is that the parameter of update is guided by this term highlighted in orange, which is the gradient of the loss function. And instead of doing that by hand, so that we have some analytical expression, which is like what typically people do mathematically, here we delegate that task to the computer by using machine learning frameworks like JAX. So just quickly, we iterate with this optimization. We iteratively change the parameters until some convergence where we have some solution. And this happens over a number of steps. And if you compare gradient descent with something like evolutionary algorithms, this is one of the key selling points. You'll get a solution in only a couple of seconds, which would be 43.7 times faster than if you were to do this with something like Galapagos in Grasshopper. So faster solutions for you to do more design exploration while satisfying design constraints. So the secret sauce here is the application of machine learning frameworks like PyTorch, TensorFlow, or JAX, which predominantly, I think, are famous for being kind of the scaffolding to prototype neural networks and do deep learning research. But the exercise we do here is to take this technology and figure out ways to apply them to solve architectural and structural design problems. Here we focus on JAX, although what I'm saying, we could do a PyTorch FDM or a TensorFlow FDM had we pick any of these other frameworks. Well, we picked JAX because for a number of reasons. One of them is that JAX is open source, written in Python, and specifically, it looks a lot like NumPy, but it's NumPy with superpowers. These are the three features I would like to highlight about JAX. One is that it gives you accelerated linear algebra, which means faster matrix multiplications and linear solves. It gives you automatic differentiation, which is essentially what got us here in the first place, the ability to get derivatives to feed into gradient-based optimizers without having to derive those by hand. while still having those derivatives be exact up to computer precision. And lastly, we also have access through JAX to just-in-time compilation, which essentially says that if you're typing some code, right, JAX has a compiler that at runtime is going to optimize it at a low level so that it can run essentially faster for multiple backends. This could be, so the same code could be optimized for CPUs or GPUs or TPUs. So one same file can run on multiple devices, which we find fascinating. The ability to have access to JAX gives JAX FDM a bunch of very interesting features. One is that, well, through FDM, we can solve this constraint from finding problems using a legendary solver that has been around for 50 years and is backed up by plenty of research. But importantly, we can also formulate constraint form finding problems with respect to all the parameters that are input to the form finding method. So this means that we can not only optimize for force densities, as many people usually do, but we can simultaneously optimize for the applied loads and for the support positions, which allows you to do interesting things like the image I show here on the right, where we can like optimize the shape of the boundary and interior of this grid shell so that we can achieve a shape that is not only compression only, but that is also planarized. And all of this happens automatically thanks to JAX FDM. We can also factor in shape-dependent loads because you are thinking of doing something like an inflatable, or finally factoring self-weight, which is a shape-dependent thing. We can actually optimize by considering those load cases. And lastly, we have access to a rich bank of constraints and loss functions that continues to grow, that includes, target lengths, target reaction magnitudes, planarization, etc. This gives you and us the ability to solve a wide array of constraint form finding problems for structures that work under compression, here denoted in blue, tension denoted in red, and combinations of the two. And each of these structures corresponds to a different problem. We can do low energy grid shells, we can do cable nets that have target lengths, we can do air supported structures or inflatables that kind of best fit some arbitrary shape, all of that with one single tool. And this is the kind of the funny part of the presentation, where I like to think that this tool is not only my precious because it's one of the core building blocks of my PhD, but also I like to see it as one rink or one tool that allows you to kind of rule all the constraint form finding problems, a general purpose tool essentially. So this is a DevDay, so I figured I needed to put something about the architecture of JAX FDM. And this is more or less the gist of it. There are two main parts. One is the backend, the other one is the front end. The backend is powered by JAX, which gives us AutoDiff and JIT. And so the other part that we use SciPy for is to actually use the optimization algorithms they have, like SLSQP, LBFGS, among others. JAX FDM has roughly 7 different modules, where in equilibrium we have like the equilibrium models, FDM, constraint form finding, goals and constraints give you access to this. This is actually a lot like Kangaroo, where you can drag and drop different kind of objectives on the canvas, excuse me. And then we have the optimizers under JAX FDM optimization, and then we have a bunch of visualizers for different front ends in this visualization module. So this is the back end, and then on the front end, right, this is the COMPAS DevDay. So COMPAS actually has been the key piece of infrastructure that has allowed us to make this kind of low-level JAX solver accessible and operationable through different front-end platforms like Blender, Grasshopper, Rhino. And so, to be honest, like as any other PhD researcher, my weekends were spent trying to connect the backend and the front end, especially because JAX sometimes has some very questionable idiosyncrasies, but that's for a different conversation for another day. So just to conclude, let me give you a taste of how the API looks like if you want to use it today. And we're going to focus on the example I've been carrying around throughout this presentation. So since we are using COMPAS essentially as an interface here, we can load a data structure from a JSON file called mesh. And this is a force density mesh. Then we set up the structural simulation, the form finding parameters, first by specifying some force densities, -2, which is compressive on all the edges. we applied a unit vertical load pointing downwards to all the vertices. And then the mesh, we assigned some supports at kind of the perimeter of the system. And then with a one-liner, we can run the form finding with FDM with default parameters, and then we're gonna get a version of mesh that is that is compression only essentially. That is fine. That's the business as usual purpose. But what if we? And then we have a viewer as well that is specializes on displaying force density objects. The viewer, add mesh, and then show. You know the drill. But now the important part here is the constraint part, right? So we can load another target mesh, and this is a standard COMPAS mesh from JSON. And then this is going to have the target shape we care about. Then we set the optimization parameters by specifying that, all the edges, we iterate over all the edges of the mesh. Then we define the edge force density as the optimization parameter, and we can set bounds to them so that, for example, the solution is compression only. So here we have a lower bound of -50 as the kind of the highest force density, but in negative that the solution can take. And then we have this kind of very small value so that the solutions then go to 0 or don't go into the tension domain. Then we define the goals, which are, the best fit situation where we have iterate over all the vertices in our mesh. And then we set a vertex point goal assigned to the vertex key over mesh, and then we get the target coordinates as like a list with 3 numbers, XYZ coordinates on the other mesh. Then we save everything in the goals list, and then we kind of compile the goals into a loss function that measures some error, in this case, the mean squared error between the solution provided by the FDM and the goals we care about. Finally, to get the solution we see on the right, we pick some optimizer, in this case, LBFGSB. Then we solve the optimization problem using gradient descent and LBFGSB by calling constrained FDM and passing as arguments the mesh, the optimizer, the loss, which has the goals in them, and the parameters. And the result of that, after a little bit of dancing, is an optimized mesh that, using the same viewer, we can finally visualize and look at the thing we see here on the right. And the nice thing, again, because of COMPAS, is that the same code could run in my terminal, but it can also run on Colab or a Jupyter notebook, or it can also run in Rhino 8, which has support for Python 3. So again, one tool, multiple visualization opportunities. So that's a wrap. Thank you for listening today. So today I introduced JAX FDM. It's a differentiable solver for fast structural design. There are benefits. It provides an automatic solution of constraint from finding problems. It's faster than your traditional genetic algorithms and other gradient-free methods. Constraint form finding is one big part that motivated this work, but actually, thanks to JAX and differentiable programming, we have other research presentations and other research papers of ours have demonstrated that through differentiability, we can connect different form finding methods together. That's something I presented last year at ISS. So essentially combining FDM and CEM. And we can also extend that to make the force density method or any other mechanical simulation really be a building block in neural networks. That's something we presented this year at iClear, a premier machine learning conference. And so essentially the sky is the limit. There is a lot of cool stuff happening, and we'd be open to collaborate and do things if you think this could be beneficial for your work. Coming up next, a new version of COMPAS CEM powered by JAX, and it's expected in summer 2025. So this is going to be using a package called JAX CEM. And we're also thinking about JAX DNA for the fall so that we can have a portfolio of differentiable solvers, namely FDM, CEM, TNA, to offer structural designers, a wide palette of things to tackle different complicated constraint form finding problems. So the GitHub, the code, if you're interested, there's a QR code in my presentation. I thank you for your time, and I look forward to hearing back from you. Thank you so much.